Alright, we're going to start scientific and engineering notation, and we want to be able to understand the difference between the two and how we write one versus how we write the other one. Alright, so what we should be able to get after this is you're going to be able to write numbers in scientific notation, we're going to be able to write numbers in engineering notation, and we're going to start using SI prefixes. You might have heard of it, System International or International System, however you want to take a look at that. But we're going to be able to do that. So in the engineering world, we do a lot of different things using SI prefixes, and those SI prefixes are tied to our engineering notation. Alright, so let's talk about scientific notation first. You might have done this in science class. It's a way we can take a really big number or a really small number, okay, and compact it so it's easier for us to write and understand. So instead of writing a number that's like 10, 15, 20 digits long, we can truncate it down and use scientific notation to make it a more manageable and understandable number. We do a lot of things like, decibel readings and earthquake readings. So when you hear like an earthquake is 4.8 on the Richter scale, that's actually like a scientific notation number versus like 4.8. And what does that really mean when it talks about the magnitude of the size of the earthquake? Okay, so we're going to take those numbers and write them. So when we do scientific notation, we have to do them a specific way. So there's a certain form where we have to write this number. It has to come in the form of A times 10 to the B. Alright, so the A is really important and the B is important here. The B is the exponent. Okay, A is kind of the value we're looking for. When we write scientific notation, though, that value of A has to be a number, okay, that's a single digit. So it has to be the number 1, 2, 3, 4, 5, 6, 7, 8, or 9. It cannot be any higher than that. So it has to be the numbers 1 through 9, okay, before the decimal place. So you cannot use 10, you cannot use 20, you cannot use 100, you cannot use 500 when you're using scientific notation. You will always have one number before the decimal place, okay, and then we're going to have times 10 to some exponent. Alright, so if we look at the first example here, it's 3.24 times 10 to the 5th. If the exponent is a large number or a positive number, okay, it's going to be a larger number. If the exponent is a negative number, so if you look at example 2 here, it's 1.435 times 10 to the minus 7th. Okay, that's a negative exponent, meaning that number is really, really small. It's much smaller than 0. So when we're doing scientific notation, if we have an exponent that's positive, it means our number is going to be greater than 0. If our exponent is negative, we're going to have a number that is less than 0. And that's going to tell us which way we're going to move the decimal point as well, whether we're going to move to the right or to the left. Okay, so that's the next important part here. So we're going to shift the decimal point. So we only have one digit. We already talked about that. So it has to be a digit 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. A decimal point. And then we can have, you know, our significant figures. We're not going to get into significant figures in here, but we're going to have our significant figures that follow that decimal place times a multiplier of 10 to some sort of exponent. Remember, if the exponent is 0, the value is actually 1. So anything to the 0 power, 10 to the 0, 1 to the 0, 100 to the 0, they're all equaling 1. Alright, so we've talked a little bit about the power of 10 is positive. Okay, the decimal point, we're going to move it a certain direction. The power of 10 is negative, we're going to move it a certain direction. Alright, so if the power of 10 is positive, okay, that means the decimal point has been moved to the left. If the power of 10 is negative, it means the decimal point is moved to the right. So we're going to go through a couple examples here so that you can understand this. So first example here, we're going to take this number 5,630 and we're going to express it in scientific notation. Okay, so what do we have to do? Well, we can only have one digit, and since this number is greater than 0, we're going to start and say that there's a decimal point to the right of 0. So we're going to move it 3 places. Why 3? Well, because the decimal point ends up between 5 and 6. Meaning if it's between 5 and 6, the 5 is on the left of the decimal point, and the 5 is a single digit when we do that. Okay, so we're going to take that and we're going to move it 3 places to the right. So if we see the number 5630, we know that the decimal point comes after the 0 and we don't use it or write it. So when we do that, we have to move the decimal place 3 places to the left in order to do that. So when we write this, you're going to end up writing 5.630 times 10, and the important part is the exponent. It's positive because the number is greater than 0, and we moved it how many places? We moved it 3. So we're going to take this number, 5.63, times 10 to the positive 3, that's how many places we moved it, and it's positive because the number is greater than 0. So that's important. Alright, let's take a look at another one. Notice this number is much, much, much smaller than 0. We have 0.000628. So in your mind, in my mind, I'm automatically thinking I'm going to have a negative exponent on this on this one, and we are going to move that decimal place as many times as we need to so that there is only one digit in front of it. That digit needs to be the 6. Alright, so we move that decimal point over 4 places, so we get 6.28, and then we write times 10, and then we have, how many places did we move it? We moved it 4, but we moved it to the right, and this number is less than 1, so our exponent has to be negative. So we're going to move that 4 places over. We're going to get 6.28, so we end up with 6.28 times 10 to the negative 4th, and the negative 4 is because the negative is because it's less than 0. 4 is the number of moves that we had to make. Okay, so that's scientific notation if we are handling a number that is greater than 1, or if we are handling a number that is smaller than 0, or smaller than 1, I guess, sorry. The cutoff point is smaller than 1 and greater than 1, not 0 as I said before. Alright, now this gets us to the important one. You're going to use this all through mechatronics. We're going to use engineering notation. Engineering notation, it's very similar to scientific notation. However, a couple different rule changes here. The rule changes are all of the exponents have to be in multiples of 3. So when we look at this a times 10 to the b, that b can only be multiples of 3. So it can be 0, 3, 6, 9, 12, 15, 18. It can go the other way too. Negative 3, negative 6, negative 9, negative 12, negative 15, negative 18, so on and so forth. So it's very important that how you move the decimal, you have to move it in chunks of 3. So remember when we did scientific notation, we could just move it however many places we need, so we needed a single digit. When we do engineering notation, we have to limit it to moves of 3. Everything has to be a move of 3. The second part is A is different here as well. With scientific notation, A could have been 1, 2, 3, 4, 5, 6, 7, 8, 9. That was it. With engineering notation, we can use the number 1 all the way up to 999. So we can have 3 digits in front of the decimal place. Okay, so that's really the difference. Let's take a look at these examples here. We have 71.24 times 10 to the third. Engineering notation. Can engineering notation and scientific notation be the same? Yes. Look at the second example here. We have 4.32 times 10 to the negative 6. That number could be written as a scientific notation or as engineering notation. So there are places where they can overlap. So make sure that we kind of pay attention to that on some of your tests or homework. I might ask you, is this number engineering notation or scientific notation or both? You have to be able to know that it can be both at the same time. Alright, but look at the third example. We have 320.49 times 10 to the ninth. So notice that we can have up to 3 digits before that decimal place, and then the exponents have to be in increments of 3. Okay, 9 is an increment of 3, or a multiple of 3. Okay, so shifting is the same way that we did with scientific notation, only we have to shift them in chunks of 3. So it's still, positive goes to the left, negative goes to the right. That's still the same kind of concept here when we move this. Alright, so we're going to take this really big number here, All right, 16346000000. All right. Hopefully I said the right number of zeros. So we're going to take this number here, and you're going to start on the right-hand side and start grouping numbers in chunks of 3. So you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going to move those over because we are doing engineering notation. And how do you know when to stop moving them over? All right, when you can no longer move a chunk of 3 and you have up to 3 digits to the left of the decimal point. All right, so let's take a look here. So we pop this out. 1, 2, 3, 1, 2, 3, 1, 2, 3, for a total of 9 moves. All right, so I'm going to take that decimal place. I'm going to move it 9 places to the left. But I would always draw like an underline so that you see what you're chunking into groups of 3 when you do this. Okay, so then you're going to get 16.346 times 10 to the 9th. So it's very important engineering notation. That has to be to the 9th. Notice we could not do 3 more moves, because we would have what? 0.016. That's not an engineering notation, because you can't have 0.0. There has to be a digit starting at 1 in front of the decimal place. All right, and just like with scientific notation, we can go the opposite direction. Notice this number is smaller than 1. Okay, so our decimals to the left, in my mind, I know that I have a negative exponent here. So that's very, very, very important. I'm going to have a negative exponent, so however many moves I do. And now I'm going to move to the right in chunks of 3 because we're doing engineering notation. Okay, so we're going to start at that decimal point, and we are going to move in chunks of 3 to the right. So when we do that, as you can see, we're going to move 1, 2, 3, 1, 2, 3, and we can't do another chunk of 3 because we can only move up to 6 points. And when we do that, okay, we can move it up and maximize that digit in front of the decimal place. Remember, it can be anything from 1 to 999. So we can use 348.6 times 10 to the negative 6 here. Why is it negative 6? 1 is it's less than 1, so it's got to be negative. 6 is the number of places we move the decimal in chunks of 3. Okay? So let's get into XI prefixes. It's a way we can shorthand our engineering notation using the International System of Units. All right, so it's more of a European, very, very similar to the metric system. All right, metrics kind of based on this way as well. We are going to be using SI prefixes in all of our mechatronics engineering courses that you're going to be taking as you go through the program here. So we'll be doing that. So it's very important that you start getting used to some of these, and you probably know some of these as well. All right, these are some of the most commonly used ones that we use on an everyday basis. Right now, right, we have hard drives that are terabyte hard drives or gigabyte hard drives. Okay, we have you have 2 gigabytes of RAM or 8 gigabytes of RAM in your computer, 16 gigabytes of RAM in your computer. You have a 250 gigabyte hard drive on your computer, or you have a 1 terabyte drive. All right, those of you that are using your Xbox or things like that, right, you need to have the games take up a lot of space now, so you have like an external memory. It goes with this. So very common stuff, computer tech world. The other stuff, we have prefixes for large numbers and prefixes for small numbers. So you need to make sure that you know every single one of these. You will be tested on them, and you will use them, like I said, all the way through the mechatronics program here. So you need to know that 10 to the 12th is a tera, 10 to the 9th is giga, 10 to the 6th is mega, 10 to the 3rd is kilo, 10 to the negative 3 is milli. We're going to use current and things like that, so we're going to have milliamps. 10 to the minus 6 is micro. We're going to use microamps. 10 to the minus 9th is nano. 10 to the minus 12th is pico. We're going to use like a picofarad capacitor and things like that. So really, really small value, but a capacitor has a really, really big charge, so it's going to impact you there. And then 10 to the minus 15, we don't really use anything that's a femto. Okay, and we represent that prefix. So tera is represented with a capital T, giga is represented with a G, Mega is represented with a capital M, kilo as a lowercase k, and the capitalization matters. It does matter if it's an uppercase or a lowercase letter. Okay, so kilo is K, milli is a lowercase m, micro is a Greek letter mu. Alright, if you write a U on your test, I'll understand what you're talking about, and we know that. Alright, nano is a lowercase n, pico is a lowercase p, and femto is a lowercase f. So there is a difference if you write a little m or a big M. That's a big difference, okay? We're going from milli to mega there. So you got to be really careful when you do this. You will be tested on all of these, all right? So here's one where we got to put it all together. We're going to do SI notation. So we're going to express the number 27,500 ohms. Ohms is a unit of resistance. We're going to be using that a lot in the electrical courses that you're going to be taking with us, and in this course a lot. So we're going to take 27,500 ohms, and we're going to use standard SI notation. So there's two steps here. All right, the first step is you have to put it into engineering notation, and the second step is you have to go from engineering notation to SI notation using the table that we have here. All right, I would make sure that that's in your notes and you kind of have that until you learn it. You will know this table pretty good by the end of the year. All right, so let's take a look. Let's look at that number, and we got 27,500. We got to put that in SI notation. So engineering notation first. We have to move that decimal place. How many places here? The most we can move it is 3. Remember the decimals after the 500 piece on the far right-hand side. If we move it 3 places to the left, we're good. We cannot move it 3 more places because that number will be less than 1. We don't want that. All right, so we're going to move it 3 places. So when we do the engineering notation, we're going to get 27.5 times 10 to the third. How many places did we move it? 3. That's why that exponent on the 10 is 3. That's how many places we had to move the decimal. And then we take that 10 to the third, and we look back on the previous table here, on the previous slide. 10 to the third is represented by kilo. So when I do this, that we replace that times 10 to the third with a lowercase k. So 27,500 ohms rewritten in SI notation is 27.5 kilo ohms. And that's how we say that. It's a 27.5 kilo ohm resistor. Alright, so that's a way where we're using, and this is international, okay? That's why it's SI. So you go over to China and you're working on electronics. They use the exact same notation we use over here. You go to India, same notation. You go to Europe, same notation. South America, same notation. All over the globe, everybody uses the same notation. Okay, it's very, very important. You're not going to go over to Ireland. They're going to use some other like sort of notation or something like that. Okay. Let's take a look at a smaller value now. Well, this is less than 1, and we have volts. We're going to convert that to SI notation. So remember, when you're going to SI, first thing, put it into engineering notation, and then use engineering notation to translate it into SI notation. So we have this number here, 0.00568 volts. You're never going to have something that small, but let's practice putting it into, I mean, you might, but most of the stuff we're going to work with is not that small. But we're going to use this voltage, okay? And we're going to convert it into SI notation. So first thing, we got to move that decimal place to the right. How many times can we do that? If we move it our first chunk of 3, because remember engineering notation, we're moving in chunks of 3. If we move our first chunk of 3, is that number acceptable? No, it'll be 0.568. Not big enough, so we got to move it another chunk of 3. So now we have to move it 6 places, and we get 568. Okay, now we can do this one. I don't ever do like the first part here with that solution. No one's going to go 0.56 millivolts. Most common nomenclature, right? We moved it 6 places, so it's 568 times 10 to the minus 6. Minus because it's less than 1. 6 because that's the number of places we moved. All right, and we have 568 microvolts. So we replace that times 10 to the minus 6 with micro. That's from the table from a few slides ago. And then we keep volts, but we don't really write volts. We're going to learn later that we're going to write a V instead of volts as we go through this. So hopefully you're going good. SI notation, like I said, Not too hard, just takes a little bit of practice. You guys will do that on your post-lecture quiz and on your homework assignments as well. Alright, so some common electrical things that we use. Alright, we're going to always talk about current, voltage, and resistance. Those are the main things that we're going to talk about in this course. And then, we got capacitance, inductance. We'll tap on capacitors. We're not going to mess a whole lot with inductions unless you take my advanced electronics course that we do with MTSU. So, power is very important. We're going to do a lot of power calculations, and then we'll talk about frequency when we're going to be analyzing signal analysis and things like that. All right, so current is amps. Okay, the current's the flow of electrons, and we're going to cover a different lecture on that. But current, the symbol for current we use is I, not C, because usually a capital C is for capacitance, and a lowercase c is used for the speed of light. So current, we use I. And the unit for current is an ampere, or we short it with amps. Okay? Voltage, the symbol for voltage is a V, and that's a unit is a volt. So we talk about you have a 9-volt battery, a 12-volt battery. That's where that comes from. Okay, resistance. Okay, that's limiting current flow. We're going to get to all that stuff when we talk about Ohm's law and things like that. Resistance, the symbol for resistance is R. Okay, and the unit for resistance is ohms, and we represent that with an omega. I know this might be confusing. It'll make sense once we start doing more examples and working through. Frequency, that's how fast the signal oscillates. We're going to get into that. You're going to analyze an oscilloscope and do all those sort of things. But frequency we use is an F to denote frequency, and a frequency is labeled in hertz, and we use Hz. So like your AM and FM radio, what you're tuning to is a specific frequency for a specific radio station. So that's where that comes into. All the symbols that we're talking about in the middle column, those are what we're going to use in our equations or our formulas to solve for things. Okay, when we write out our answer, we're going to express them in units. So that's where we're going to use the A, the V, the omega, the hertz, the F, the H, and the W. That's where that comes in. So like I might have 12 volts, I would write 12V. All right, I have, a 100 ohm resistor, I might write 100 and then an omega. Our electricity operates at 60 hertz, so you would write 60 Hz. Okay, you'll get used to it as we go on. Let's finish these out though. Capacitance, the symbol for capacitance is a large C, and we use capacitance as a farad and represent it with an F. Inductance is an L, and we call those henries. The unit of inductance is henries. Alright, and power is a capital P, used in all appliances, the utility company. That's how you pay your electric bill, things like that, all based in power and kilowatt hours, is a watt. Okay, so a capital W. So all the units there on the right hand side, those are all named after old dead guys that did this stuff a couple hundred years ago. Alright, so that's somebody's last name. That's where they came from, and we're going to talk about them kind of as we go through the course as well. So those are common symbols and units that we are going to be using in here all the time. You're going to use it at the next level next year when you're doing all the mechatronics courses, so you need to get to know all these, the SI prefixes. So just to recap what we've done, we've learned how to write in scientific notation, we've learned how to write in engineering notation, we've learned how to take engineering notation and put it into SI prefixes, and then we've learned about some basic electrical signals and units and things like that.